Alright, hey AP Chemistry. So I just wanted to post a brief video, it's probably be 15 minutes, about titrations and skills and what we're getting from this data when we put it together. So part A's of both these labs, I've made you titrate and take the pH every 1 or 2 milliliters. So let's pretend like I have a pH probe in here. And I also put acid-base indicator in here, just so you can see I know when to stop the reaction. But notice how my technique is when I'm titrating. I have it slowly dripping, right? Slowly dripping, and I'm supposed to stop it every 1 milliliter and record the volume. So I'd be like, okay, that's 5 milliliters. Let me take the pH with a pH probe. So if I use somebody's pH probe from today, I put that into the solution, right? And I get the pH, and boom, I record the volume that I used and the pH at that time. And then notice how, I don't know if you could see on this flask, but I have some pink liquid, or I have some sodium hydroxide that ends up around the flask. You could continuously add distilled water to the sides of the flask. You probably want to continuously rinse the side of the flask because you have some sodium hydroxide solution that splashes and ends up on the side of the flask. And so some of you notice that this endpoint is so sensitive that even a drop could change the color of the solution. So I would just continuously wash slightly with distilled water just to make sure that if any sodium hydroxide ends up on the side, it goes in and reacts. And remember that my hydroxide's always reacting with my acid. I also like to put the flask underneath the nozzle of the burette and squirt the nozzle onto the tip of the burette. Now it looks like my video is a little bit too bright. If you make it a little bit darker, you'll see that I had the nozzle here and I put it underneath. I'm just gonna titrate this a little bit far to go past to like that pink endpoint. And I could already see that I'm putting in a lot of solution and the pink spreads out a lot. Okay? And then just a side note, and this ends up on the AP exam a lot, you could use burettes for volumetric analysis and it gives you precise data. So burettes are a good way of getting like exact volumes. So when you do that AP style question this week and it talks about what piece of equipment would be the best to get volume, if you're given a burette, that would be the best time or best piece of equipment to get the exact volume. Other than that, a volumetric flask is good to give you the volume. So notice what I'm doing now. I'm allowing it to drip and I'm letting it swirl. I'm probably going to rinse the flask and the side of the nozzle of the burette to make sure that I got all sodium hydroxide in here. And I'm going to drip some more into here until I get that faint pink endpoint. And I'm able to adjust the nozzle so it's only slightly dropping a little bit. And I don't know if you can see from here, but the pink is getting really far, like it's spreading out further and further. So you should continuously swirl, swirl, swirl until that pink gets quite severe, like it spreads out into the entire solution. So I'm almost there. I probably need one more drop, and then I'll probably be at my very, very faint pink endpoint. I guarantee one more drop is going to make this dark pink or that light pink. Okay? So probably one more drop, and boom, right? Almost. I don't know if you can see it from here, but another drop probably, and that'll probably do it. All right, just do that. All right, probably one more drop. Okay, I probably put 3 in there. And now, it's, oh man, this is really close. And notice how close you get. Like I put 3 drops in there, it gets really dark pink, gets a little bit faint pink, and then it goes back to colorless. That means you're getting really, really close, right? So I just rinse the side of that. If you see that happening, if you see the dark pink getting spread far apart, that means that your endpoint is getting really close. And you'll note that with the pH meter, that the pH is getting quite high. All right, and so now it looks like, oh, look, the pink, it got pink for a while. I probably need like, I gotta get one more drop in there. All right, probably, all right. I keep on saying one more drop, but this is the technique that you use for that titration. All right, and so now you can kind of see that I'm at that very faint pink endpoint. Okay, and so let me move over now to if I had recorded this volume and pH every milliliter. Okay, if I record the volume pH every 1 milliliter, here's what you don't want, by the way, so I just wanted to show you this. This is quite dark pink. That means I've gone beyond my endpoint, and the phenolphthalein indicator changes color when I'm at a pH greater than 9. If I'm titrating an acid with the base, and I actually had hydrochloric acid in here, if I titrate a strong acid with a strong base, the pH at the equivalence point should be 7. If I'm titrating a strong acid with a weak base, my pH will be less than 7 at the equivalence point. And if I'm titrating a strong base with a weak acid, my pH will be greater than 7 at the equivalence point. Now I could already tell that this is my strong acid, strong base, and I went way past the equivalence point because the pH has got to be at least 8 or 9 here. Okay? All right, so now I want to look at and kind of sketch out a titration curve and how you read and interpret them. So you're going to be making a titration curve, and on your x-axis you have volume of NaOH added. Okay, and that's usually in milliliters. And so that's the volume that came from the burette. Overall, it looks like I added about 12.5 milliliters, and that was way beyond my endpoint here. Every time you added your volume of NaOH, I asked you to record the pH. So you got a volume that you added and a pH. Volume, pH. So your table looks like this. Volume, pH. So it probably was like 0, and then it was like 2.88, and then maybe it was 1 milliliter, and then it went to 2.97, dot, 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 dot. That's an example of the data that you collected. When you plot this graph, it should look something like this. Beautiful, right? And on my y-axis is my pH. Okay, so I'm going to move this back slightly so you can see that. On my y-axis, I have my pH. And this is known as a titration curve. And so there are several parts of this titration curve that's very important. I have this beginning, and so if this was a weak acid, let's pretend like this was a weak acid. In the very beginning, I have pH that's resistant to change. Okay? And in this region, with my pH being resistant to change, this is known as my buffer region. And this is for titration of a weak acid. And this is like in your acetic acid lab. Okay, so your acetic acid lab, the study of acetic acid, you're going to get a titration curve that looks a little bit something like this. So I have a pH resistant area, and I know it's resistant to change because it's flat. My pH is kind of slowly staying constant, and then it's going to peak up. In this pH range, my concentration of HA, my acid, is equal to my concentration of A minus. And if you remember what A minus is, that's my conjugate base. And so in this region, when my concentration of HA is equal to A minus, this is when my pH is equal to something known as my pKa. Okay? And just so you know, the pKa is the negative log of the Ka of this acid. And remember, K, if you remember from the last chapter, is the equilibrium constant. So Ka is the equilibrium constant, or the acid dissociation constant, of this acid. Okay? Then, over here, at probably halfway in between the top and bottom, this is known as my equivalence point. Equivalent point. And that's when my concentration of my acid, or my moles, actually I'm going to say moles of acid. I'm going to say my moles of my acid is equal to my moles of my base. And in this case, it was the NaOH. Okay? And so remember, I titrated this acid with a known concentration of base and a known volume. So let's say I plotted this volume. It was 5, 10, 15, 20, 25, right? So the way that I have this set up, it looks like at this equivalence point, I use 15 milliliters of this concentration of hydroxide was 0.1 molar of 0.1 molar NaOH. Okay? So at the equivalence point, that tells me that my acid has fully reacted with my base. My moles of my acid is equal to my moles of my base. If I have a molarity and I have a volume, I could easily solve for moles because molarity times volume in liters is equal to the moles. And remember, it's my favorite equation. So my molarity of my base here times my volume of my base gives me my moles of my base. Now, if I know that at this equivalence point, the moles of my base is equal to my moles of my acid, now I know that this is equal to my moles of my acid. And if I want to figure out the concentration of the acid, remember, if I want the concentration of HA, it's going to equal to the moles of HA over the volume of HA. Right? If I want that concentration, I need the moles of HA over the volume of HA. Well, if I know that my moles of HA is equal to my moles of base here, I already got my moles of HA. Where do I get my volume of HA? Well, that's why I told you, oh, make sure you bring a graduated cylinder over to the fume hood, because I'm giving you 10 milliliters of this acid. Where did these moles of acid come from? The volume of the acid that you titrated originally. So this volume of the acid is the volume that you took from the fume hood, or that I gave you. So if I want to figure out my concentration, it's whatever moles I titrated divided by the volume of the acid originally. And so that's how you find your unknown concentration. You need the equivalence point to figure that out. Also, simplified, there's this very fancy equation, MAVA equals MBVB. And if you remember, this looks kind of like the dilution equation. MAVA is molarity of the acid, or concentration of the acid, times the volume of the acid, is equal to molarity of the base times the volume of the base. And now you use this only if the mole to mole ratio is 1 to 1. 1 mole of acid is equal to 1 mole of base. Remember what MAVA is. Remember that molarity times volume is moles. This is why I love this equation, because what does this equation really say if you were to change the units? MAVA is saying moles of A is equal to moles of B. That's what this equation is saying. All right? So this is how you read and interpret a titration curve for data. If you didn't use an acid-base indicator, it's okay, as long as you took the pH every milliliter or so, because you could easily figure out the concentration of the acid or the amount of acid you have using the titration curve. So I'm hoping this was a quick and helpful way of looking at and doing titrations and doing the data and calculations. I'm probably going to post another video just zooming in more on the titration and doing a little bit of math required for your study of acetic acid. Alrighty, so if you have any other questions or concerns, let me know. You could comment in the video, or you could comment in the remind and ask for any clarifying questions. My expectation to you is going to be you need to know how to do titrations, and you need to know how to understand titration curves in order to answer some questions.